Hello students, welcome back. Let us resume our discussion in section 1. Previously we went through power functions, or 4 cases, but the last case was no big deal because it's just a composition of all those previous cases. For example, what do you mean by x to the 3/4 power? You can rewrite it as the 4th radical of x to the 3rd power. X to the 3rd power we studied already in case A, and 4th root we studied in case B. Here's another example. X to the negative 5/3 power. Negative power, so we have fraction. This power goes to denominator. And then we have 3rd radical and 5th power. So 1 over x to the 5th power, or 1 over x to the 5th power, that's something we studied in part C. And then 3rd radical we studied in B, like that, etc. And here is a program that gives you some randomly selected powers within a certain bound. So 4/5 power, 1/2 power, in this case 2 over 1 power, so it's the 2nd power, 4/3 power, negative 4/3 power, and so on. We have various things like this. You play with that. Okay, so much for the general case. Not very important by itself. Next, 1.2, some other functions. Okay, none of them is very important, but let's spend a bit of a time in absolute value function. Defined like this. X is already positive, then stay x. If it is negative, then make it positive. How do I do that? Take an extra negative to make it positive. So, x is greater than or equal to 0, then y equals to x, diagonal line. And when x is less than 0, y equals to negative x, the other diagonal line. And absolute value is always non-negative, 0 only at 0, so we have graph only above the x-axis, or the y-coordinate value has to be positive, or at minimum 0 when x is 0. And then finally one more thing, at 0 we have a cusp. Instead of having some smooth roundings like these kind of graphs, we have a cusp, abrupt change of slope. That causes a good deal of problem for, okay, never mind. Let's not go too deeply into calculus. Here's a feature. That's it for absolute value function. Next, floor function. The greatest integer, not more than x. For example, if x is, let's see, a certain decimal expression, (5.17), then this is 5. And then this is negative 7.24, then that is negative 8. The greatest integer, not more than x. So if you got negative 7, it's actually bigger than this. And then if this is pi, that's 3.14, isn't it? So you get 3. Oops. And then if this is negative pi, then negative 3.14 something. So we get negative 4. Not negative 3. Negative 3 is actually bigger than negative pi. We have to go down to negative 4. Graph like this. And then ceiling function is similar, but smallest integer, not less than x. So we have to round up for positive integers. So for example, if this had been 19.567, that's 20. If this is negative 7.41, whatever, ceiling, we have to go up, etc., etc. That kind of thing is called ceiling function, and graph looks like this. If you compare that with floor function, compare blue and brown, in the exactly same interval, they differ by 1. Here 0, here 1. Next we have 2 here, but we have 1 here, and so on. Okay, nothing else here. Oops, nothing else here. Alright, let's go to piecewise defined function. Sometimes we define a function piece by piece, interval by intervals. Okay, and here we define g of x is x squared plus 4x plus 3 when x is less than or equal to -2, and x cubed plus 2x squared plus 1 when x is greater than 2 but less than 1 or equal to 1, and then this expression -2x squared plus 4x plus 2 when x is greater than 1. Basically we are defining 3 different functions and 3 different intervals. -infinity to -2 we have first graph, -2 to +1 we have the second graph highlighted in red, and +1 to infinity we have the third graph highlighted in green. Let's see, do I have, yeah, okay, I have a graph here, -infinity to -2, blue graph. If you use technology you can do that, and -2 to 1 we have red graph, and then 1 to infinity we have green graph. But let's see, when x is equal to -2, so same inequality belong to blue, not in red, so solid is blue. This one is just emptied out. So function value at x equal to -2 is right here. Looks like that's going to be -1. And then here, the function value at x equals to 1 is, oh no, not green. I have to go to red region to see that, because we have semi-inequality here. Here, strictly greater than 1. Here, less than or equal to 1. So I have to go to red region and plug the value into this. In the end, though, no change because we have continuity. Red, and then without any jump, green just took over. So luckily there was no problem here. But at x equal to -2, this blue versus red, there was a gap and there was a jump. These kind of examples are called piecewise defined function. You can define anything piece by piece, but the intervals has to be subdivided well without any contradiction, and then at each interval we have to have a well-defined function. There's some rules like that. Always the boundary point can be cumbersome. Okay, alright, so much for section 1, library of functions, which actually is a continuation from lesson 5. Now in lesson 6 we're going to study linear functions and linear models from section 2, which are well, the simplest case is power function with n value, the power 1, but of course we are going to consider a little bit more difficult cases as well. Pay particular attention to piecewise defined models here, because linear models by themselves tends to be too simple, so piecewise models may be useful there. One final comment, I have a optional section 0 about lines, but that's reproduced from section 4. But even in section 4 it was a review from elementary algebra and intermediate algebra. So if you need, you can review those, but here I'll assume everybody knows everything about lines.